Great. Good morning again. So this morning we've got a couple of talks. First one is about synchronization. I'm going to go a bit deeper into some of the other synchronization constructs that are available in OpenMP. So why do we need this? So just remember from yesterday, we need to be able to synchronize actions from different threads on shared variables. So we need, in particular, to ensure the correct ordering of reads and writes. If we need to ensure that one thread writes a value before another thread reads it, then we need to do some synchronization between the threads to make sure that those actions happen in the order in which we intend, and that we don't end up with a race condition. And we also need to protect updates. If we're doing a sort of read, modify, write type action on a shared variable, then we need to protect those from the potential for multiple threads trying to do that at the same time, because those updates are not atomic by default. Okay, so we've already seen and talked a bit about barrier synchronization. So just to recap, this is a full synchronization point between all the threads in the current parallel region. So no thread can proceed past a barrier until all the other threads have arrived at that point in the program. And we've already seen this in action because there's this implicit barrier at the end of the work sharing directive. So do for sections, which I haven't actually talked about and nobody really uses these days anyway, so don't worry about that, and single directive, for example. Okay, so there's these there are these barriers implicit in those constructs. However, sometimes we want to add an explicit barrier inside a parallel region, and there's a way of doing that with the barrier directive, no surprise. Okay, so this, unlike everything else we've seen so far, is a standalone directive. It does not have a block of code associated with it, and so it really just says, no, at this point in the code, do a barrier synchronization between all the threads. No surprises in the syntax. Okay. Exclamation mark $OMP barrier in Fortran, hash pragma OMP barrier for C and C++. One thing we do have to be careful of, though, if we're using barriers and we have any sort of complicated or non-trivial control flow inside our parallel region, is that we have to make sure that either all threads encounter this barrier directive or none of them do. Otherwise, if some strict subset of the threads reaches the barrier and the other ones don't, then that will just deadlock. Okay, the threads that were waiting at the barrier are expecting all the threads in the parallel region to turn up at some point, and if they never do, then those threads will never get released from the barrier. So this restriction is true for the work sharing directives as well, for parallel loops. If we have a loop with a do or for directive on it, then in the same way, we have to make sure that either all the threads in the parallel region actually reach the parallel loop construct, or none of them do. Otherwise, again, we will end up with deadlock, and we'll also end up potentially with only part of the loop being executed. So a little bit tricky to contrive a reasonable example that fits in a few lines, but I'll try anyway. Okay, so I'm supposing that I have some algorithm where I want to consider my my threads as a ring of processes. Okay, so if I'm inside a parallel region, if I get my my thread ID and store that in my ID, and then I say, okay, I want my neighbor. I want to have a concept of my neighboring thread, and my neighboring thread is the one with the ID one less than me. And if my ID is 0, then my neighbor is the last thread. Okay, so it's and my neighbor is the thread with ID 1 less than me, and at the beginning it wraps round to the end. Okay. Then suppose that I'm doing some calculations and I store some value in an array A based on my ID. So I calculate something, okay, and store that value in the element of this array A corresponding to my thread. And then at some point later, I want to read the value in A that my neighboring thread calculated. So this is a case where I really have to be careful to ensure that this write here has happened before the corresponding read to the same element of A, which is going to occur on a different thread. So in order to respect that dependency and avoid race conditions, one straightforward way of doing that in OpenMP would be to put a barrier directive between the write and the read of A. So that makes sure that all these writes have occurred before any of these reads can happen. So it really does ensure that when I come to read my neighbor's value, I'm absolutely guaranteed that it's already been written by that other thread. So particularly if you've done any kind of message passing programming or other types of parallel programming, the question might occur to you here, well, can I not, this is overkill, right? I don't need to wait for all the other threads. I only need to make sure that my neighbor has executed this statement. I don't care about any of the other threads, but I'm still, if I have a barrier here, I'm still waiting for them anyway. And the answer is, well, yes, absolutely, that's true. And OpenMP does not provide a straightforward way of doing pairwise synchronization between threads. So there really isn't a good way in OpenMP to say, okay, at this point, I want to wait for one other specific thread to reach some point in the program. That kind of synchronization is not really supported in OpenMP in a straightforward way. So in OpenMP, we tend to use barriers to do this, and it is somewhat overkill. Or it can be somewhat overkill in the sense that we end up waiting for threads that we really didn't need to wait for. But hey, that's part of the design of OpenMP, and in some sense we have to just live with that. Okay, and here's the same example for Fortran programmers. Okay, any questions about barriers? Andrew?
Yeah, so can you just flip back to the previous slide?
Sure.
Okay, so are we making the assumption here that these threads are ordered for this example?
Well, I've written the program to construct an order here.
Right. Okay.
There's no implicit order here, but threads have sequential numbers. Okay, starting at 0 and going up to 1 less than the number of threads in the parallel region. Okay, so I'm basically programmatically imposing this neighbor structure here.
Right. Okay.
That's not implicit in OpenMP.
Okay. Thanks.
Okay, so I'm just constructing that as part of my code. Okay, so if you remember yesterday, we talked about the master construct as a way of making a piece of code be executed by thread 0 only. And master does not, so unlike single, master does not have an implicit barrier at the end of it. But quite often, this that turns out to be another case where quite often you want to, or you need to add an explicit barrier is at the end of a master region. You often end up in the situation where the other threads are have some dependency on something that's happening in that master region. So you want them to wait and ensure that the master region has executed before they carry on executing the rest of the parallel region. So that's probably that's one of the commoner cases where explicit barrier directives are necessary. Okay, so the next synchronization construct I want to talk about are critical sections. So a critical section is a block of code which can be executed by only one thread at a time. Okay? And so this is a mechanism that can be used to protect updates to shared variables. Again, so OpenMP is pretty predictable. You can guess what the syntax looks like. Okay, so Fortran's critical and end critical, enclosing a block of code. C++ hash OMP critical with a structured block. So a simple example here would be, suppose I have, suppose I'm building up a list of objects or a list of structures. So I have a loop where I'm calling some function to create some new structures, and I want to add those on to the end of a list. Okay, so it could be a linked list, for example. So suppose that the creation of these structures is computationally expensive. So I'd like to exploit multiple threads to do the creation, but when they come to add their new item to the end of the list, then only one thread at a time is going to be able to do that. Otherwise, I'm going to end up with some race condition and some horrible mess going on if multiple threads try to add items to the list at the same time. So this would be one way or a convenient way of doing it. So okay, I can take my loop, I can apply a combined parallel for directive to the loop so that it executes in parallel, and then each thread, for each iteration, threads will independently be calling create item. So those calls can happen in parallel, and then but then they enter critical section. So only one thread at a time is able to append the new item to the list. So critical does not imply any ordering here. So threads can enter critical in any order. So what happens in practice is that the first thread that reaches the critical will enter it and execute the block of code. Any other threads that arrive in the meantime will wait their turn to enter the critical region. So it doesn't imply any ordering in which the threads execute this block of code. It just ensures that only one thread at a time can execute it. Okay, so let's have the Fortran example as well. So that's a simple example where we just have one critical region. We can actually have more than one critical region inside a parallel region. And in that case, the semantics are that if any thread is in one of these critical regions, then no other thread can enter any of the critical regions in the code. Okay, so if we have multiple critical regions, they ensure mutual exclusion from each other as well as from themselves. Okay, so so take this example a little bit further. Okay, so instead of just adding to a list, suppose we have a stack of tasks, a stack structure, and we're pushing and popping. Okay, so have a parallel region, multiple threads executed, and then inside. Okay, so while there's still something to do, then each thread will pop a new item off the stack, go away and do some heavy-duty processing on it here, and then if that processing may create a new item to go on the stack, in which case we can. So if p new is not null, then we're going to push that new item back on the stack again. Okay, and then we check to see if the stack is empty or not. If it's not empty, then we carry on around and pop a new one on, and so on. Okay, so it's basically just doing simple operations. So again, we want, although it's fine for, I'm assuming it's fine for different threads to be calling process on different items at the same time, but I only want one thread at a time accessing the stack. But this time, instead of just a single access to the list, we've now got two places in here where the stack is being accessed. There's the pop call here, and there's the push call down here. So I want to protect both of those, and so OpenMP critical regions do exactly what I want here. If I put a critical around the pop and a critical around the push and the is empty, then that protects correctly. Because, for example, if one thread enters the first critical region and is executing the pop function, and in the meantime another thread arrives at the second critical region, it will block there. because although there may be no other thread in the second critical region, there is a thread executing the first critical region, and that prevents another thread from both from entering the first critical region and the second one. Again, same deal in Fortran. So it might occur to you, think, well, what happens if I have two different shared data structures and I want to use critical sections to protect them? Does this sort of mutual exclusion from all critical sections, is that not overkill? How would I get around that? And there is a mechanism for doing that. You can give critical sections a name, so that appears as a you can give them an arbitrary name, which appears in brackets after the critical directive, and then you only get mutual exclusion from critical sections with the same name. So it's not a particularly common case, but there is a way of handling that. Any questions about critical? Go for it, Andrew.
Okay, can you just flip back again 2 slides? That's it.
That one?
Yeah. So so the thread enters that first critical region.
Yeah.
That blocks all of the threads going through. So that P new process, that can continue independently. That's not covered by the.
So that's outside the critical.
Okay.
The critical ends at the end of the curly braces.
Right. Okay.
Yeah. So we think what happens at the beginning. Okay.
Yeah.
So one of the threads, we don't know which. Okay,
yeah.
will be the first one to arrive at the first critical.
Yeah.
Yeah. So they will go in and execute the pop. Any other threads that arrive at the critical will get blocked.
Okay.
Okay.
But they can continue down to.
No, they can't. Right? They can't go anywhere until the first thread gets out of the critical.
All right.
Okay. So threads cannot. Threads arrive at a critical. They will block there. They do not skip over it.
Right. Okay. Okay.
Right. Yeah.
So the thread has to complete that P next step before it goes on to the P new step.
So the first thread, once its first thread has completed the pop, it exits the critical. Okay. At which point some other thread can go in.
Yeah.
And in the meantime, the first thread can go ahead and go off and do the processing.
Okay.
Okay.
Yeah.
So and then when the next thread comes out, it can also carry on doing the processing. So you have to kind of imagine here that if this is going to be a worthwhile thing to parallelize, then process has to take a much longer time than push or pop.
Yeah.
Okay. So you have to be spending most of your execution time inside this process. Otherwise, it's just not going to be worthwhile. Right? You're going to spend all your time. The threads are just going to spend all their time sequentialized in the critical sections.
Right.
Okay. So once things have got started, what you hope is that for most of the time, you've got multiple threads all executing the process function concurrently. And then once in a while, they finish. go into the critical.
Okay.
Okay.
Right.
But
so the order in which threads arrive at that first pragma critical region
is unknown. Okay.
Is unknown. Yeah. Is not
unknown.
necessarily also the same order at which they arrive at the second critical region.
No, could be completely different. Yeah.
Right. Okay.
Yeah.
Right. Okay. Thanks.
So there's absolutely there's no implied ordering implied order in which the threads execute the critical.
Okay.
Okay.
Thanks so much.
And there's no reason why say you could perfectly end up in a situation where some threads execute a critical section many more times than other threads.
Okay.
There's no reason, there's no reason why they should necessarily, depends on the control flow. There's absolutely no reason why the threads have to execute there's no reason why every thread has to execute a critical section the same number of times.
All right. Okay. Yeah. Okay. In my head, I had this sort of sequential sequence building up.
Yeah. No. There's no ordering here.
Right.
Okay.
It's first come, first serve, so to speak.
Absolutely. I'm going to talk about locks a bit, but if you're sort of familiar with concepts of locks, then essentially what critical is doing is just implementing a global lock. Okay.
Yeah.
So there's a single lock which a thread acquires when it enters the critical, and it releases the lock at the end of the critical, and only one thread at a time can hold the lock.
Okay. It's a bit like
that's kind of another. That's probably how it's implemented under the hood anyway.
Right.
Well, that's potentially a conceptually helpful way of thinking about it.
Yeah. Okay. I'm just thinking of network protocols where you've got token ring, where only one computer can communicate on the network if it holds the token.
Yeah.
So
that's
a
similar kind of concept. Yeah.
Yeah. Okay. Thanks.
So Sahil asks, is this not like single? And the answer is no. Okay. But it is easy to be. It's easy to get confused between critical and single. Okay. So let me explain the difference. If I have let me go back to the list example with one critical section. Okay. For critical, okay, every thread that arrives at the critical will execute this block of code at some point. Okay. They will be executed one at a time. Okay. Only one thread can execute it at a time, but every thread will take their turn to execute that block of code. Okay. So that's not the same as single. What happens if this, for a single block, what happens is that the first thread to arrive will execute the block of code. All the other threads don't execute it. They skip over it and wait at the end. Okay, so it kind of feels like it ought to be similar, but it's actually not. Okay, so for critical, it just makes sure that every thread will execute the block, but only one at a time. For single, only one thread will execute the block, and the other ones skip over it and wait. Okay, again, the waiting is different. Okay, so there's no single has this implicit barrier at the end, which critical does not. Okay. Any other questions? Okay, so the next one is atomic. So atomic is used to protect a single update to and it only applies to shared scalar variables of basic type. Okay, with the qualification that here a scalar variable can be an element of an array. Okay, so not an entire array or a pointer to an array, but scalar variable here includes elements of arrays of basic types. Okay, and the atomic directive, in its update form, applies only to a single statement. Okay, so syntax is straightforward. It's just for Fortran OMP atomic, and the statement has to look like this. Okay, so it has to be something x equals x operator some expression, or the other way around, or it may involve intrinsic functions. Okay, so you say like x equals x plus something. Okay, or x equals max of x and something. Okay, so and then there's then a list of allowable operators and intrinsics. And same deal for C and C++, except it has to be a binary operation. So it has to be x, for example, x plus equals something, or x multiplied equals something, or the sort of x plus plus or plus plus x short forms, and those are the allowable binary operators. So okay, so what you can do is slightly different between Fortran and C here. Or the allowable things are slightly different. Okay. Now, this is different from critical in a couple of ways. The evaluation of the expression on the right-hand side is not done atomically. Okay. So if I have multiple threads encounter this atomic statement, then they can both evaluate. So we have multiple threads all evaluating the expression on the right-hand side at the same time. Okay. The only thing that is protected is the modification of the variable on the left-hand side. But an important feature of this is that it really is just protecting, the protection really is just on the accesses to the memory location of the thing on the left-hand side of the statement. So that means it can be more efficient than using critical. In the case, for example, if the thing on the left-hand side is an array element, then different array elements can be protected separately. So if I use critical, then it means that even though the array elements on the left-hand side may be different elements of the array, the threads still have to wait their turn. If I use atomic, then that gives the implementation the freedom to implement it in such a way that updates to different elements can happen at the same time. So we'll see that more clearly with an example in a moment. The other thing to note is that there is no interaction between critical and atomic. So you cannot you cannot protect a shared data structure with critical in one place and atomic in another place and hope that they mutually exclude in the same way that multiple critical sections mutually exclude. So there's no mutual exclusion between atomic and critical, even though you may be trying to protect the same shared variables. Okay, so here is a short example. So what this calculation does is it is basically, if I have a graph here, so a graph is just a collection of vertices joined together by edges. What I want to do is compute the degree of every vertex in the graph, and the degree of a vertex is just the number of edges that are connected to it. So, for example, this vertex here has degree 3, this one has degree 2, this one has degree 1. And the way I'm going to do that is I'm going to run a loop over all the edges, and then I'm going to add 1 to the degree count for the vertex at either end of the edge. Okay, so if we ignore the OpenMP for a minute, just see what the underlying code is doing. It says, okay, so I have a loop over all the edges, and say so for this edge. Okay, I go to vertex, so I have an index for vertex 1 corresponding to the vertex at one end of the edge. So I use that value to index the array of degrees, and then increment it. And then I do the same thing for the vertex at the other end of the edge. So at the end of that, I will end up with the degree counts for all the vertices. Okay, right. Suppose I've got a very big graph with millions of vertices and edges. I'd like to execute this in parallel. So can I do that efficiently? Well, one reasonable way to try that would be to use the atomic directives like this. Okay, so I use parallel for in the loop. So I'm going to divide up the loop iterations between threads. But then I have to protect against the unlikely but nevertheless possible case where I have 2 threads operating on edges which are connected to the same vertex, and they could potentially, so 2 different values of j could both involve accesses to the same element of the degree array here. Okay. So there is a potential race condition there I have to protect myself against, and a way to do that would be to use atomic here. Okay, to say that these updates are atomic updates, so only 1 thread at a time is allowed to modify this memory location, which is effectively on the left-hand side of the statement. Obviously, these are ones without equals statements, but you can see why it's still the left-hand side. Okay, so that potentially works okay because the implementation can still allow updates to different elements of this degree array to happen at the same time. So it's not absolutely guaranteed the implementation does that, but you have a good chance that is going to work in most OpenMP implementations. And so you will get some parallelism out of this. So that's different from what would happen if we use critical here instead. If we use critical, then only 1 thread at a time could execute either of these statements. So that means we would actually sequentialize the entire computation and add a whole bunch of overhead for the critical sections as well. Okay. So this is kind of an extreme case where critical would be a disaster, but atomic should actually work reasonably well. This is a bit of an abstract example, but this pattern also occurs in molecular dynamics applications a lot. So if you think of instead of vertices and edges, you think of, okay, so these are particles, and where I have an edge, then there's a force interaction. And so you typically compute, your computation would be computing forces between pairs of particles, and then you need to update the total force on either end of the interaction. Okay, so Sahil asking, could I reiterate why critical would be bad? Yes, okay. So if I use critical instead of atomic here, then for every single update, every thread would be blocked while another thread was executing the update. So I could only ever have one update happening at a time with critical. Whereas with atomic, as long as these are different elements of the degree array, then the updates can happen concurrently. Okay. Any questions about atomic? Any more questions about atomic? Okay, so the last thing I'm going to talk about here is lock routines. So most of the time you can do what you want in terms of protecting shared variable updates with either critical or atomic will do the job. But sometimes we need a bit more flexibility than what's provided by critical. Or we have a case where we'd like to do atomic updates, but the thing we're updating is not a basic type in the underlying language. Instead of being an integer or a floating point value, it's some structure, it's some data structure or object that we want to update. So sometimes we need more flexibility, and in that case, what we can do is we can use the lock routines. So the way these work is the lock is a special variable that can be set by a thread, and once it's been set, no other thread can set it until the original thread which set the lock has unset it. Okay. So the other way to think about it is, lock has a concept of ownership, where a thread sets the lock, it gets ownership of the lock. When it unsets it, it releases ownership of the lock, but only one thread at a time is allowed to own the lock. In OpenMP, setting the lock can either be blocking or non-blocking. So again, this is some additional flexibility. The uses, almost nobody ever uses the non-blocking case. Okay, so it's possible. So instead of waiting for the lock to become available, you can just return a true or false value as to whether you succeeded in acquiring it, and then go away and do something else. nobody ever does that, but just to be you'll see it in the interface in a slightly odd way. So that's why I want to mention it. I'll come back to that in a moment. You have to, in OpenMP, you have to initialize locks before you use them, and then you can destroy them when they're no longer required. Basically, just to release any memory that was associated with the lock. And supposedly they're supposed to be opaque objects. You're not supposed to try and store any values in them. They're probably just plain old integers underneath in the implementation, but you're kind of not supposed to know that and try and store any values in them. Okay, so the interface for Fortran, so to like the other runtime library routines, we can get access to them via the omp_lib module. So the functions we have available are init lock, which does the initialization, set lock, so that's the blocking version of setting lock. The weird one, and why I'm kind of even bothering to mention non-blocking sets, is that the naming is weird here. Okay, so there's a function called Omp Test Log, which confusingly is the non-blocking setter. Okay, so test lock does not do what you expect. You might expect from the name, it says you can use it to test to see whether the lock has is currently set or not. That's not what it does. Okay, confusingly, test lock is the non-blocking set, and it returns true or false depending on whether the attempt to own the lock was successful or not. Okay, so basically, you might see this in the specification or in other OpenMP, other descriptions of OpenMP lock routines or whatever. But just to emphasize that it probably doesn't do what you first think it might do, and you can probably almost certainly safely ignore it, because nobody ever wants to do this. Well, virtually, I've never seen a real application code that uses non-blocking locks. Okay, then there's the unset and the destroy. Okay, so if you're old-fashioned Fortran, then locks are basically have to be integers, basically 64-bit integers. But okay, we're not using old-fashioned Fortran, so the OMP-lib defines you a data type for these called OMP lock kind, which you can use to declare the lock variables. So in C++, we have the same set of routines: init, set, test, unset, and destroy. And again, we get access to them through the omp.h header file, and there's a defined type in that header file. There's a defined type for those to use to declare those things. Okay, so I can potentially use locks to solve the same problem with my degree of every vertex case here. Okay, so instead of using atomic, so in practice, this particular case, atomic's almost certainly going to be more efficient. But so there are cases where you can't use atomic because you're trying to update something that isn't a basic type in the language. So that's where you might want to use an array of locks instead. Okay. So what I'm going to do here is I'm going to declare an array of locks, okay, and the size of that array is equal to the number of vertices. So I'm going to in my program logically associate one lock variable with every vertex. Okay, so the lock variables themselves are not directly or explicitly associated with any other memory locations in your program. That's something that you have to take care of. If you want to do that, you have to take care of that programmatically. Okay. So I need to initialize those locks. So here I'll just have a loop over all the vertices, and for each vertex, I am going to initialize its corresponding variable in the lock array. And then when I come to do the computation, what I can do is every time I want to update an element in the degree array, then I will set the lock in the corresponding place in the lock array. Okay. So just to emphasize, I am explicitly and programmatically making this association between a lock in the lock array and this element of the degree array. But there's no implicit association between the lock and this memory location. So for this element of the degree array, I set the corresponding lock, do the update, and then unset it. And then again, I do the same thing for the other element of the degree array corresponding to the other vertex. Set the lock, do the update, and then unset the lock again. Of course, this is how you handle locks is completely up to you in the programming. So, but perhaps a more again, if you think about the analogy with particle dynamics, molecular dynamics, then you might think, okay, so rather than depending on how your data structures are organized, many applications of that type will have some data structure or an object which represents a particle, which may contain a bunch of different fields and values associated with that particle. And if you have data structures like that and you want to use locks, then it would be a natural thing to do would be to add a lock to that object or data structure, so that every instance of that data structure comes with its own lock. So whenever you try to update a value in that data structure, you set the lock that belongs in that data structure. But again, that there is no even if you do that, you still have to make that logical association between that lock and the data structure. The lock does not automatically, in any sense, protect everything else that happens to be in that data structure. Okay. Any questions about locks? Okay, so using locks is to say sometimes you're kind of forced into it because there's no other good solution, but you do have to be pretty careful in the sense that it can be very easy to write code that will deadlock. Okay, especially if you get into code that has if you get into branchy code. So you're acquiring locks in one branch, you have to make sure that there's always, that the corresponding unlock is always going to happen, or the corresponding unset is always going to happen somewhere. So you can quickly get into situations writing code where it becomes very hard to reason about whether your code is always deadlock free or not. So they're quite a powerful tool, but they're also quite dangerous as well. Okay, so this is a good point to introduce the next of the practical exercises. I say, please just work through them at your own pace. But the next one is in fact a very simple molecular dynamics code, and so this is the computation, as you would expect, is dominated by the calculation of force pairs. So there are a bunch of other routines in the code, but you can ignore those. Just concentrate on what happens in the forces function. So what you can do is you can parallelize that with a parallel loop directive, and then use critical sections to protect the corresponding updates. So recommend you start off using critical sections. Okay, so you have to think about, you also need to think carefully about private and reduction variables on the parallel loop, and you might also think about what's a suitable loop schedule for this problem. So there's a few other kind of revision topics here as well. But then you can think about, so once you've got something working with critical, say, okay, can you improve the performance by using atomics or using locks? Or in fact, this pattern is also, there's also another way to solve this pattern, and that's using a reduction array. So that's yet another way of solving this kind of, implementing this kind of pattern. So okay, we'll get on to practical sessions after our coffee break later on. So any other questions about synchronization? Yeah, go for it.
Yeah, okay. If you create a feature and you use a barrier, is there a pattern that you use or a paradigm to get a result from the feature before the barrier or within the barrier after?
Okay, so OpenMP does not support features. It's the simple answer there.
Okay.
Okay.
Yeah. There might be a reason. So yeah.
Okay. Yeah. So no, that's not, features are not part of the way that OpenMP implements parallelism.
All right.
Okay. So that's the simple answer. If you trying to mix, say, what are you thinking of here? Features from what, C++ threads?
Yes. Yeah. Exactly.
Yeah. Okay. So trying to mix features from C++ threads and OpenMP in the same application code is dangerous, shall we say, or at least not guaranteed to work. The exception to that, which is probably okay and will normally work fine, would be to use C++ atomic classes. They probably, in most circumstances, they will work okay with OpenMP. But other features that involve essentially anything that's going to involve creating threads, or could potentially involve creating threads, mixing and trying to mix and match features from OpenMP and features from C++ threads is really not guaranteed to work. And you might be in a situation where it works with one compiler and not another compiler. So you probably want to avoid trying to do that.
Okay, so if I look at the use case, I would use a combination of atomic classes to realize it. Okay,
yeah. So again, that there's still no guarantees, but I would kind of expect that works. That's going to work fine. You shouldn't run into any problems in practice. Okay. So neither of the specifications really says anything about the other. Okay. So there is no specification which says how OpenMP threads and C++ threads should interact with each other. So you just get what a particular implementation will do, and there's no guarantee they do sensible stuff or that different compilers will do the same thing.
Thank you.
Okay, let's take a 5-minute break before the next lecture. Okay, on with the next topic then, which is actually just a collection of more or less unrelated topics, none of which are long enough for a full lecture. So the bits and pieces I'm going to cover here are to talk a bit about nested parallelism, say something about orphaned constructs. So basically, what happens when we have essentially what happens when we have function calls inside parallel regions. Say something about thread private globals, and then a little bit about timing routines. Okay. Nested parallelism to start with. So nested parallelism is supported in OpenMP. So what happens is, if we're already inside a parallel region, inside a parallel construct, and we encounter another parallel construct, then a new team of threads will be created. So there's the potential for every thread to itself create a new team of threads. So usually the implementations don't create extra threads by default. Depends on the implementation. You usually need to enable this explicitly. So either by setting the OMP nested environment variable to true, or by calling the OMP set nested library routine. In practice, you don't often need to use nested parallelism. It can be useful in situations where we have algorithms where there are multiple levels of parallelism. but the topmost level doesn't have enough parallelism to keep all our threads busy. So it might be particularly useful in cases where we're trying to use a lot of threads, trying to use a lot of cores, and we have multiple levels of parallelism available in the application. So it's usually disabled by default because enabling it does incur some additional essentially bookkeeping overheads in the OpenMP runtime. So don't turn it on just because, okay? Because it can negatively impact performance if you turn it on and don't use it. Okay. If nested parallelism is disabled, what that really means is that your code, if you have code with nested parallel regions, it'll still execute fine, but the inner teams will only contain one thread. Okay, so your code will still execute, but only the outermost parallel region will create threads, and the inner ones will just execute on one thread. Okay, so reasonably simple example is suppose that I have two loops here. So I have a loop over values of I, which set some values in an array X, and a loop over J, which sets some values in Y. And okay, so there's no reason why there's no reason in principle why I need to do all of this loop and then do all of this loop. I mean, that's kind of what you would naturally, the way you would naturally write it, and the simplest way to write it, you would just do this loop first in parallel with multiple threads, and then this loop in parallel with multiple threads. But in principle, there's no reason why you cannot try to execute both loops in parallel at the same time, as well as using multiple threads in each loop. So what you could do is you can have an outer parallel region, okay, and I'm going to arrange for example, for that to have two threads here because I've got two separate loops, and we'll talk in more detail. There are multiple different ways to set the number of threads in nested parallelism. So I will cover those, but for the moment, let's just gloss over that and assume that I've arranged for the outer parallel region to contain two threads. So then if I get my thread ID and I say, okay, if I am thread number 0, then I will create a new, okay, so remember, this is a combined parallel region and do directive. Let's get my pointer here. So this will create, this is a parallel region. So in principle, this can also create new threads. So thread 0 in the outer parallel region can create a team of threads to execute the I loop. And at the same time, thread 1 in the outer parallel region can also create another team of threads to execute the J loop in parallel. Okay, so you can get a structure like this. Okay, so I have the original master thread, an outer parallel region with two threads. Thread 0 itself creates a team of threads. I've shown 4 threads in total for this, for the I loop here, and then at the same time, thread 1 in the outer region is executing, it also creates its own team of threads to execute the J loop. So this kind of structure of nested parallel regions is possible to do in OpenMP. Okay, so there are various different ways of controlling the number of threads that get used at different levels. Simple way to do that is to use the environment variable. So the environment variable OMP num threads actually takes a, you can actually take a comma separated list of values. So this will determine the number of threads at each level of parallelism. So for that previous example, I can say OMP num threads equals 2, 4, and that will use 2 threads at the outer level, and then 4 threads for all the parallel regions at the next level down. And I can extend that to more levels if I have more than 2 levels of parallelism. Other mechanisms, if you want more control, are to use the OMP set num threads function or the num threads clause on the parallel region. So let's have a look at another example that uses those. So these are useful if you're in a situation where you want your inner regions to use different numbers of threads. So, for example, I could say, here's a slightly different example. Here I've got nested loops. So I have an outer loop with 4 iterations. So that's probably, if that number 4 is fixed, then there's no way that I can use, I can use more than 4 threads if I just parallelize this outer loop. But if I parallelize this outer loop, okay, and then also have a parallel for directive on the inner loop, so then for every iteration of the outer loop, I will create a new team of threads to execute the inner J loop here. And in principle, I can, I can choose, maybe I can pre-store them in some array. Okay, so for every value, in principle, for every value of I can call OMP set num threads, and that will use that number of threads to execute the next parallel region that's encountered. I'm also using OMP set num threads to set the number of threads to the outer parallel region. So I'm setting that to 2. So what happens in this case is that I get 2 threads executing the I loop in parallel. So each thread will itself execute 2 I iterations. And then for every iteration of I will get a new team of threads created with this value of threads, which can be different for every value of I in principle. And so it's a slightly weird contrived example, but you do have that, that amount. You can in principle control the number of, use this function to control the number of threads for every instance of every parallel region that gets executed in the code. So you can explicitly control the size of every team of threads that gets created. Alternative to doing that is to use the num threads clause, which appears on the parallel directive. So you can explicitly request a certain number of threads at the point where you create the parallel region using the num threads clause. Okay, so as mentioned here, the value of, if you use set num threads, that overrides anything that you set in the environment variable. And then if you use num threads clause, that in turn overrides everything in the environment variable and anything that you previously set with OMP set num threads as well. So the num threads clause always takes precedence. Which of these mechanisms you use is really a matter of software engineering convenience. So there are cases where you might really want to have it explicitly stated for every parallel region, or there are cases where you might just want to call, you might just want to call OMP set num threads once somewhere in your code, or once or twice somewhere in your code, and not have to care about passing thread numbers around to use in the clauses on every parallel region. So it really depends on your code structure and how you want to handle it. I should though say a word of warning about using OMP set num threads, okay? Because this call can happen anywhere in the code, and it sets the number of threads that for whichever thread that makes that call, that's the number of threads that will be created by every parallel region encountered by that thread in the future. So it's possible to bury these calls away, to squirrel a call to OMP set num threads away somewhere in some obscure function, and it can be very unclear whether when and where this function is being called and how it's being used to control the number of threads. So I have and it's again this is I would also although I've done it here, I would for illustrated examples, I would also be very cautious about hard coding numbers of threads in these calls. Okay, it's always probably best to have them as an input value from somewhere. Whether you're reading it from command line arguments or you're reading it from a file somewhere. Okay, you discourage hard coding numbers of threads. I've seen an application. I've seen at least one application where somebody's done that, and it's caused a serious performance issue, which took a fair bit of work to figure out what was going on, because it said this. There was basically a hard-coded call squirreled away somewhere in the depths of the code. And it was very unobvious that was what was determining the number of threads being used rather than the environment variable. So from a software engineering point of view, just think carefully about how you're using this and do something sensible. So make it obvious to anybody who's using the code, how and where the number of threads is actually being set. Okay, so there's a bit more control that you can have. So with nested parallelism, it's easy to end up in a situation where you're creating lots and lots of threads, and you may be it's easy to have them to end up with more threads than you have cores available to execute them, which may not be ideal from a performance point of view. So there's an environment variable OMP Thread Limit. So this limits the maximum number of threads that can be running at any one time. So you can basically use that. You can basically use that value, match that value to your available hardware resources, and then no matter how many nested parallel regions you have executing concurrently, you're guaranteed that you're never going to be having more than that number of threads running at the same time. You can also control the maximum depth of nesting. You can say, okay, I only want, maybe there's 3 levels of nesting in the application, but I can say, okay, I'm only going to allow 2 levels to be actually active and create new threads, and the 3rd level will execute on 3rd level parallel regions will always execute on a single thread. And then there's a bunch of utility routines to help you kind of navigate your way around this. So basically, you're creating this sort of hierarchical tree of threads. So you can use, there are some functions that help you navigate around that tree. So there's OMP get level, so that tells you the level of parallelism that you're currently at. So that will return 0 in the sequential part of the program. That will return 1 in the top level parallel region, and then increasing values as you go down the nest of parallel regions. The variation of that is get active level, which basically says, okay, that returns the level of parallelism, but it doesn't count levels which are inactive. In other words, doesn't count teams that only contain one thread. It only counts levels where you have more than one thread executing in the parallel region. Then you can also figure out where you are in the tree by using this. So get ancestor thread num, and you pass that a level. So that will return you the thread ID of this thread's ancestor thread at any given level. So in particular, if you want the ID of your parent thread, then you would call OMP get level, subtract 1 from that to go up 1, and then pass that to OMP get ancestor thread num. And similarly, you can also get the team size at higher levels as well. There's one particular pattern that I want to mention here where you might be tempted to use nested parallelism, but at least in some common cases, there's actually a better and more efficient solution, and that's where we have nested loops. So the kind of use case I'm thinking about here is the use of what's called perfectly nested rectangular loops. Okay, so that's a bit of terminology. What is that? Well, let's unpack that and see what that means. Okay, the perfectly nested bit means that all the executable statements occur inside the innermost loop. So there aren't any code statements, say, for example, between the first and second fors, and likewise there are no executable statements between the end of the inner loop and the end of the outer loop. So that's what perfectly nested means. The rectangular bit means that the indices of the inner loops don't depend on the iterators of any outer loops. So for example, if instead of j less than m here, if I had j less than I, so the bounds of the j loop depended on the value of the iterator in outer loop, that would not be a regular loop. Okay, so that would actually be triangular, if you like. That's it's talking about the shape of the iterations, the multidimensional iteration space. Okay. So provided we have perfectly nested rectangular loops, but that is quite a common use case, then instead of, and we want to parallelize more than just the outer loop, for example, because the outer loop doesn't contain enough iterations to keep all our threads busy, then we can use this collapse clause. We can have a single parallel for directive before the outermost loop, and then have a collapse clause on that. Okay, so what does that do? Well, the argument to the collapse clause is the number of loops to parallelize, the number of loops to collapse, counting in from the outside. Okay, So in this case, I've got 2 loops. So I need to tell it to collapse both of these together. What does this actually do? Well, what it does is it implicitly transforms this nest of loops into a single loop, a single long loop. So in this case, it will have n times n iterations. So it'll generate that one implicit long loop, and then it will parallelize that and schedule that as though that's what the for directive applies to. Okay, so it implicitly creates a big long loop, and then it divides the iterations of that implicit loop between the threads in whatever way that the schedule clause specifies. So yeah, so this kind of pattern is useful if, for example, if n is order of the number of threads, so maybe maybe a bit less, or maybe equal to, or maybe a bit more than the number of threads. So that just parallelizing the outer loop may not either exploit all the threads or may not have good load balance. So for this particular use case, this is going to be more efficient than using nested teams. Okay, so you could implement this using nested parallel fors, and then do all the and then have to control the number of threads at each level and so on. But that involves a whole bunch of overhead to do with creating those extra teams of threads and the barra synchronization at the end, and so on and so on. So it's so for this particular use case, which is reasonably common, there is this collapse clause solution, which is better. So even if you never use nested parallelism, this is a potentially useful tool to know about. When we have nested parallelism, then synchronization gets a little bit more complicated, because then when we have synchronization constructs, we have to think about, okay, so which set of threads do these synchronization constructs apply to? Okay. So that depends, because for barriers, so either explicit or implicit barriers, those only affect the threads in the innermost enclosing parallel region. Okay. So there is no way to have a barrier that involves threads coming from multiple different teams. So a barrier will only synchronize threads in the currently enclosing parallel region. On the other hand, all the other synchronization constructs like critical regions, atomics, and locks, they affect all the threads in the program. Okay, so they apply to all threads that are executing. So that can be slightly problematic if you want to implement mutual exclusion within a team but not between them. Then using critical might be a problem. Okay, so that's another case where you might want to use locks and have a separate lock for every inner team, for example, rather than using critical, which is effectively a global lock across all the threads. Or you might be able to use atomics. Okay, any questions about nested parallelism? And use cases are relatively rare, so we don't see nested parallelism used a great deal in real applications. I think it's good to be aware of it, even if it just prevents you doing it accidentally. just to know that that's what will happen if you, or that's that's what's going to happen if you have parallel regions inside parallel regions. And so that's that may not be what you intended. Okay, so next topic is orphaned directives. So this is again a piece of terminology which refers to the case where we have directives that are present in functions which are called from inside parallel regions. Okay, so simple example we think about here is where we have a parallel region that has a function call inside it, and then that function in turn has a loop inside it, and we want to parallelize that loop. Okay, and essentially the basic message is that just works fine. Okay, so what happens here is that the parallel region creates the threads. Every thread will make a call to this function thread, and then once we're inside thread, then the for directive indicates that the loop iterations should be divided between the threads. So that all works kind of as you would expect. Okay, that's great because it prevents us from having to break our programming style just to add OpenMP. It can be slightly confusing. So what happens if you might wonder, what happens if I also have a call to thread here, which is not inside a parallel region? What happens to this directive? So there are some rules here, but effectively what happens is that this directive, if you call this from outside a parallel region, then effectively what happens is that this directive gets ignored. Okay, and the whole loop will be executed by the master thread. So I have to qualify that very slightly because, for example, if you have things like private or reduction variables, variables in private or reduction clauses, for example, on this directive here, then the creation of those private copies will still happen. And in sort of rare cases, more particularly with C++, with object-oriented programming, you could be in for a surprise that if I have an object in a private region, then the default constructor for that object will get called. So that might not be what you expected. Okay, so yeah, the private, if you've got any private copies specified, then the creation and destruction of those private copies will still happen anyway. Okay, there's also some extra rules we need about data scope attributes as to what happens when we have functions called inside parallel regions. So essentially what happens is that if we pass variables through the argument list, they inherit their data scope attribute from the calling routine. Well, at least if we're passing by reference. Yeah, so we pass which is what happens in Fortran anyway. Okay, but if we're essentially passing by reference, passing by pointer, passing by address, then if it was private in the parallel region, then it'll also be private inside the called routine and so on. If we have global variables, So, or in Fortran, common blocks, which nobody much uses these days, but you might still see them lying around in old-fashioned Fortran 77 code, or module variables in more modern Fortran. Those are shared by default, and unless we do something special, which I'll come on to later. And then what about local variables which are declared inside the called function? Well, if they are static in C or C++, or if they have the save attribute in Fortran, then they will be shared. But otherwise, all other local variables inside the call, declared inside the call routine are private. So there are these extra rules that determine when things are shared and when things are private. Some of these rules might seem a little bit arbitrary, but if you understand a little bit about what's going on under the hood with the way that the languages handle data, is essentially data can either live on the heap or on the stack. And when we have a multi-threaded program, we have a single shared heap, but every thread has its own stack. So effectively, what's going on here is that if variables that are stack allocated you will get a copy for every thread, and variables which are heap allocated are shared. So that's effectively what's going on underneath here. Okay. Which brings us on to thread private global variables. These are a necessary. These are necessary in some cases just to make parallelization of large, old, application codes tractable. So if you like, they're a necessary evil, but you should not use them unless you really have to, would be my advice. Okay, so but sometimes to avoid you having to rewrite large chunks of your application, it can be convenient for each thread to have its own copy of variables with global scope. Okay, so this tends to occur in more old-fashioned application codes that effectively try to do their own memory management, that effectively allocate workspace as global variables, and then use that and modify those variables somewhere deep down in call trees. If you're trying to parallelize code like that with OpenMP, then it just can be convenient to deal with that by having every thread have its own copy of those variables. Okay, so we can do that, and what happens if we're outside a parallel region, or if we're in a master directive, then the accesses to those variables refer to the master thread's copy. Otherwise, they refer to the copy in the calling thread. So the way we do this is we use a thread private directive, which essentially comes after all the declarations. So this directive is essentially associated with the declarations of the variables rather than their uses. because they're global variables. It applies to all their uses throughout the program. And so for Fortran, we can have a list of named common blocks or module variables or saved variables. And basically this directive must come after all the declarations. Okay, and there's this nastiness with common blocks where they get declared in multiple, they get declared wherever they're used. So wherever your common blocks are declared, you have to have the matching thread private directive as well. In C and C++, we also have a thread private directive, which takes a list of variables. So that has to happen, that directive has to be a file or namespace scope, so essentially outside of functions. And it has to happen after all the declarations of the variables, but before any actual uses of them in functions. And there's some other restrictions as well, which I won't go into. And then associated with this, then there is a clause which applies to parallel regions called copy in. So this allows, what this does is that it copies the values in the master thread's thread private data to the copies in all the other threads at the start of a parallel region. So it basically means that you can, it's a convenient way of ensuring that at the start of the parallel region, all the different copies of these global variables contain the same values. Okay, as I say, it's good to know of their existence. It might be the only tractable solution if you're trying to retrofit OpenMP into typically old application code, but I would certainly not I would not ever design an OpenMP, design a code to use OpenMP thread private. It's just not a nice thing to do. Okay, any questions about that little section? Andrew.
Okay, so when dealing with the common blocks, I'm more familiar with Fortran than I am with C.
Sure.
If you're copying the common blocks into each thread, do they then become static variables, so you can't change them within the thread?
You still have a copy in every thread which you can modify it to your heart's content. Okay, so the only thing that copy in does is that at the start of the parallel region, whatever values were in the master thread's copy get propagated into the copies on all the other threads.
Okay, so
which is just a convenience, because that's maybe what you want in some cases.
Yeah.
But you don't have to use that. Okay, you can just use, you can just start off with uninitialized. Otherwise the other threads copies will be uninitialized, and you have to initialize them inside the parallel region.
So what happens when all the threads return to the master thread, to that common block that got copied? Does it just get deleted?
No, those copies persist. Okay, so the master thread's copy is not changed. The other thread's copies don't disappear. They persist, and in normal circumstances, which I will qualify in a moment, you can then reuse that. You can then pick them up again in subsequent parallel regions.
Right.
So the values will persist between parallel regions. So that happens. That works as long as you are at the outermost level of nesting. Okay, so you only have, it only works at the top level of parallel regions if you have nesting. And it doesn't work if you change the number of threads between parallel regions.
Okay.
But as long as you have the common case where you just have one level of parallel regions and all the parallel regions use the same number of threads, then the thread private copies of common blocks will persist between different parallel regions.
So are they, so the common blocks must then have an identifier to link to a thread then?
Yes, but it's not explicit. Okay, so I cannot go around accessing the copies in other threads.
Right. Okay.
Okay. So it's there. You are. Each thread is just referring to those copies using the name of the variable, and the only thing a thread can access is its own copy.
Okay. Right. Hopefully, I won't have to go down that route, but just in case.
Yeah. So I would think twice or three times before you go down this route with an application. But it can just it can just be a way of getting around having to. The alternative might have to be passing these things all the way down a complicated call tree. Right? Is to make private copies at the is to make private copies of these things on a parallel region, and then pass those private copies around everywhere through argument lists. And the prospect of doing that to a big complicated code might just be intractable.
Yeah, it might be better just to rewrite the code.
Well, there is that, right? but that is a a fairly high level design decision that you may be faced with if you have code that does this kind of thing. Okay, that has global variables or common blocks that you want to modify inside parallel regions, and in such a way that you're not going to have different threads modifying different parts of arrays or something. That's fine. You can just get away with in those cases. You can just use the single global copy. But there are cases, so where what I was thinking of is where you're basically creating some temporary workspace and accessing that as a common block. That's the kind of use case where you can't have a single copy and have multiple threads use it, because you'll just end up with race conditions.
Right. Okay. Thanks much.
Yeah. I'm very happy if you have a particular application code in mind to spend some time with you looking at it next week, if that would be at all helpful. So, offers on the table. No guarantees as to whether I'll be able to tell you anything sensible, but I can at least try and help. And no obligation, but if that would be a useful thing to do, then I'd be very happy to do that. Okay, last little topic: timing routines. Okay, so OpenMP supports a timer routine as part of the runtime library, which is quite convenient to use. It just returns the current wall clock time relative to some arbitrary origin in the past, and it returns a double precision 8-byte floating point value in seconds. So it's a little bit more convenient than some other clock routines that do something different. And you can also, you're not guaranteed what the precision is. Most implementations are pretty good, so down at the microsecond or sub-microsecond precision. So the precision in most implementations is pretty good, but you can ask it what the precision is. There's this OMP get W tick function, which will tell you what that basically tells you what's the smallest possible interval between calls to the timer routine. Okay, so you would just use it as you would normally use a timer routine in your code. You call it once, store the value, do whatever thing it is you want to time, and then call it again and subtract the previous value. Just something to be aware of, because we're now in multi-threaded world. So in principle, timers are actually local to a thread. So if you want to guarantee consistency and sensible results here, then if you're subtracting two values, then both those calls should have come from the same thread in order to be able to guarantee that you've got consistent clocks. Okay. So the bit of the exercise that's, well, there's actually two bits. You can use, you can implement the Mandelbrot example with nested parallel regions. That's quite an interesting exercise. You can also take the molecular dynamics example and use orphaned directives. So you can basically say, okay, I'm going to hoist let's hoist the parallel region outside of the forces routine into the main program, and see what happens. Okay, in this case, it's not going to impact the performance, but the idea is to see how it affects the data attribute scoping, how it affects how you handle private and reduction variables. Okay, at the end of that, I've managed to overrun slightly again, for which my apologies. Does anybody have any final questions on these topics? Okay, in which case let's allow ourselves our full half hour break, and William and I will be back at 11:40 for the next practical session, and I will talk through the first one or two exercises. Talk through the solutions to the first one or two exercises at some point during the next session. Okay, be back soon. Okay, hi everybody. So again, please just ask if you need help with the practical sessions. It would be useful though if you could just give me a rough indication of what, how far you've got so far and what you're working on. So if you could just type in the chat window and say which exercise you're currently working on, that would be helpful, and I can decide how far to go with talking through the solutions. Okay, great, thank you. So it looks like most people are still working on exercise 2, so I'll leave that for the time being. Maybe wait till this afternoon before I talk through a solution and let you have a chance to work on it. If you're struggling or just want to ask, or you just want to check that what you're doing is sensible, please just just let me know, and we can go into a breakout session, and you can share your screen with me, and I can take a look at what your code and what you're up to. So please feel free to ask about that, and don't just keep beating your head against a brick wall if it's not working out for you.